Hello again. Tonight we're going to do another photons and smoke related presentation. This is an update. I changed some things, tried to improve them. I'll point out what the shortcomings were, the improvements, and the end result. Today I posted the photons and smoke video to the Broward Astronomy YouTube site. So if you want to understand the overall project and what is he doing, it's there. Device information, the test rig that I set up. I found that some of the smoke exited the chamber even when the photon flux, the RGB LEDs were turned on. It affected the smoke, but I couldn't get the photons to completely contain the smoke within the test chamber. But less smoke was coming out with the LEDs on than when they were off. So it's having an effect, but maybe I could explain why the smoke was still coming out. If you remember, the LED strip was kind of in a spiral to get overlap between them, and that left this kind of corkscrew, and I think that's what was happening. And still there was a slight 2 millimeter separation between the LEDs because the strip doesn't have them jammed close to each other. The individual LED chips have a 30 hertz refresh cycle to keep the power consumption down. So when it's off, that could let some smoke out. And my bench power supply kind of tapped out at 4.8 amps when I really needed 5 amps. So I had to get a specific power supply for it. They don't cost that much money these days, but just something to fix. And it was difficult for me to capture pictures in infrared. I thought, well, the smoke particles would be hotter than the ambient, but it's Florida, so they're not that much hotter. So the infrared wasn't really picking up good imagery when I was testing. So I said, maybe I need to push more air, more smoke out the chamber. So I looked at a different kind of pump. I was using a fish aquarium pump. So I looked at a medical device air pump, little tiny air pump, and yeah, push more air out. And I need to switch from an infrared camera to a visual camera in order to maybe get a better look at the smoke. So switch to a 10 amp, 12 volt power supply, switch from a 2.5 watt aquarium pump to a 5.4 watt medical device pump, switch from infrared USB camera to the camera on my Samsung Galaxy S5 mobile phone. Yes, it's an antique S5. And then I added kind of a stiff card, 110-pound yellow card behind the test chamber to try and get more contrast between light and the smoke, because the smoke is white. So here's the first round changes. On the left, you can see the new and improved power supply. It looks like a power supply now. And you can see that I have my digital multimeter, my DMM, right at 12 volts. The thing in the middle, that's the new pump. You don't see an inlet because it's a one-way pump. They do make two-way pumps you can use as pressure or vacuum. I hooked that up. And on the right, we have the negative result. You can see by the white in the center, the LEDs were on, but you can also see smoke swirling out the top. This is with the LED corkscrew inside. And I noticed that when the LEDs were not on, the smoke kind of puffed out, but when the LEDs were on, the smoke kind of twisted and swirled out. So I think it was swirling. So on the left, you can see the row of LEDs inside the white area where the arrows are, and it was turned off, and you can see like a puff of smoke. So the smoke would build up in the test chamber and then just blow like, not a smoke ring, but a little puff of smoke. But when the lights were on, the smoke didn't come out as a puff. The smoke came out as this very thin, vaporous swirl. And so I took a picture down below of the LEDs with the lights power turned down really low, down to like 6 volts at about 50%. And you can see the individual LEDs. And then I drew a line like, this is where the smoke's leaking out, but because the smoke is being pushed by the radiation reflection pressure from the photons, it's causing the smoke to swirl. So I need to fix that.
Have you confirmed that temperature is not affecting it? I mean, I know LEDs are cool, but there's got to be some little increase in temperature from them.
And we'll actually get into that a couple of slides down, but you're correct. It is something to pay attention to. So I thought, well, I need to pack the LEDs closer together and get them brighter white, so not like cycling every 30 times a second. They do make all kinds of LED forms. So I was using the smart LEDs, but I couldn't get them packed densely enough. And so I said, well, what about a matrix panel, like a little display? But I looked at the LEDs and there's still 2 millimeters between every one of them. So I couldn't do that. How do I get them even closer together? And that's where LED filaments come into play. Adafruit refers to them as nOOds, like noodles, LED nudes, not NUDES, but NOODS. The way that they feel is they have a little electrical connector on each end, but the LED strip in the middle is very silicone covered, like floppy. So it's very limp noodles. They're monochrome and you can get them in different colors. Internally, the LED chips are gallium nitride. So they can be very small and put out a lot of power, a lot of photons. And the particular ones that they use to make white are actually blue. And then the outside layer of this flexible tube made of silicone has a yellowish phosphor on it. And if you've seen some of the latest inexpensive LED light bulbs for home use, if you open them up, they're actually nearly ultraviolet. They're very, very deep blue on the inside. And then the globe that covers them actually has a yellow phosphor coating. And the particular wavelength of blue going through that phosphor coating makes the phosphor fluoresce at a very bright white. So that's your final color. So these filaments are blue on the inside, so I can calculate what their photon output is. And then the yellow phosphor on the outside, I pick the brightest, hottest, whitest ones I could find. They make them at 6,500 Kelvin, and they're not color changeable. The brightness is adjustable, but I said I want the maximum brightness. So the individual filaments are just a long, flexible silicone, and the chips inside of them, if you look at the bottom left of the three pictures, you can see the individual little white squares. That's how big the LEDs are. They're 1 millimeter by 1.2 millimeters, and they're actually on sapphire. They refer to it as chip on glass. So it's not like a little printed circuit board. There's a very thin substrate of sapphire, and then that's attached to a rod of silicone. And then there's a silicone tube that goes on the outside of it, and that's what they coat with the yellow phosphor. So they're very wimpy noodles. So you have this filament that has lots of LEDs on it. And I chose the longest one I could get, which was 300 millimeters. It's supposed to be powered by 3 volts. They'll actually max out at 3.1 volts. And the actual power draw per filament is about a half an amp, 530 milliamps. And it'll spit out 1.643 watts, 160 lumens per watt of white light. On each end, there's 7 millimeters worth of metal connection tabs. The tabs are identical, except one of them has a little tiny hole in it. That's the positive terminal. And the one that doesn't have a hole in it is the negative terminal. Some of these filaments just have like one strip of LEDs that goes around the inside. And that means that if this little flexible noodle gets twisted, then the LEDs won't be shining outward. You have to make sure they're laid down correctly so that all the LEDs face the direction you want them to. There's some that are, I guess, bleeding edge, newer stuff that are much more expensive, that they have just like LEDs all the way around the rod on the inside. But that was too new stuff for me, and I didn't see that there was a lot of proven suppliers for it, so they were too expensive. So I stuck with the one string of LED chips on the rod. So you have to pay attention to how they're rotated. So the 3 pictures at the bottom, the one on the left is with the power on very dim, but looking at the bottom, like the underside, the side that's not going to be illuminating, you can see the individual LEDs. At that same voltage, if you turn it around the other way and you're looking at the yellow phosphor side, you can't see the individual chips, and that's the good part. And it's fairly bright. And then I cranked up the voltage to 3.1 volts from half that. And yeah, they're very bright. You can see how the ruler that I was using for measuring actually was very brightly illuminated from the filament. So now I had to make changes to my test rig. This is all the specs and how many photons per second and how you have to pay attention to rotation and all those kinds of things, and what size the collar was. Remember, I was using a Bita spice jar, plastic jar for my test rig, and I had to make a new 3D printed cylinder and rims for it. So I did that, and I stuffed 4 of these filaments inside that collar. And this is the assembling it. and then how I had to trim it and make it fit and dress the wires. And it goes on and on. Use CA cement to hold it together, then plastic cement once that's done. And here's the pictures. Everybody doesn't want to see the text, they want to see the pictures. Picture one, top left. The two circles at the top those are the outer rims, and then the one at the bottom is the center cylinder. So you have a center cylinder and a rim on the top and a rim on the bottom. I lined it with double face outdoor grade foam tape, and then I drilled holes so that the wires that connect to the individual filaments could be dressed outside the collar. And I thought, this will be outdoor grade tape. It'll be really sticky, and I can just press the filaments in around the inner edge. The silicone is very resistive to being attached by glues. So I pulled off the red tape that was on the other side of the double face tape, and it was very sticky, but only to my fingers. It was not at all sticky to the LED filaments. And you can see in picture 2B there's 2 holes. There was 8 holes around the collar. And then you can see what one of the filaments looks like. I had to attach positive and negative terminal wires to them, and then I used heat shrink to avoid them getting flexed and broken off. And then the next picture shows I got all of the filaments wired up, all the wires hanging out, and all the filaments were hanging like dangling spaghetti underneath. I had actually dressed the filaments around the inside, and they chose not to stick to the tape. So they just like came out the bottom. So when I went to put the rims on, I stuffed them all back in there, and they look kind of chaotic there, but I actually pushed them to the outsides to make a hole through the center, about the size of my index finger. And then I said, do they still work despite me like bending and twisting and connecting wires and stuff? And yep, still very bright white. With all filaments running at 3.1 volts, the total power consumption was just over 3 amps, about 9.5 watts. And the picture on the right, I turned on the flash on my camera so that there would be enough background light to see the individual filaments, because if I didn't have the flash on, it was just it's the arc reactor again. It was just a white glow and you couldn't see the individual filaments. So I had to redo my test rig. The incense burner is still the same, although I did make one change to it. You can see the new pump there instead of the aquarium pump. The test chamber there on the right behind the yellow card, that's the contrast card. Because the wires stick out the sides, it doesn't go all the way down into the test chamber. It just sort of seals around the top, and that's fine. Apparently with the added pressure from the new pump and the smaller opening on top of the test chamber, it was getting enough back pressure that smoke was actually coming out the top of the test chamber around the incense stick. So the fuzzy picture down the bottom right there is I took a red candle and I melted wax and I dripped wax around the incense rod once I lighted it. So on the picture on the left, you can see the little white ash at the tip of the incense rod, and I had dripped wax to seal the smoke generation chamber. And then we got a lot more smoke coming out, and I was still using my my DMM, my voltmeter, to judge whether that cheapy power adapter on the left, when it said 3 volts, was actually producing 3 volts and not like 7 volts. Oh, and I took a clip-on light and put it opposite the test chamber to create a better contrast background for the smoke to come out and be detected. So here's the observations. Lights off on the left. It's kind of hard to make out, but it was still just sort of smoke leaking out. Not a puff, just continuous, very low density plume coming out of it. So it's hard to see in the imagery, but that grayish you see just to the right of the hole in the top, that's smoke. And then on the right is with the LEDs turned on. And you can see that, wait a minute, I thought this was supposed to stop all of the smoke particles from coming out. Turns out Diane had a point. The LEDs got warm, and the heat from the warmth of the LEDs actually was pulling up on the air coming out of the chamber and drawing the smoke out. And once the smoke got above the opening, the heat and the light were actually pushing the smoke up. So given that I have a higher flux, a higher density of photons, and there was a little bit of warmth coming off of the filaments, it was actually pushing more smoke out than with the lights off. And it was pushing more smoke out in a continuous movement than it was with the LED spiral, because that was kind of a swirl coming out. This was just like jets of smoke coming out. Unexpected observation. Those are always good in science because they tell you, you think you know what's going on, but you don't. Here's the summary of this project. I'm kind of done with it at this point. Yeah, I tried using the multi-LED RGB strips, and they swirled the smoke. The 30 hertz refresh rate didn't seem to affect anything. With the RGB LEDs, we get a swirl. It didn't fully contain the smoke, but it did affect the movement of the smoke particles. Prefer there be no gap, and that maybe if we can get some that don't have a 30 hertz refresh rate, and go for broad spectrum white light. So the filaments were fine, but I had too much white light coming out. If I had shorter filaments so that they didn't go around a couple of times, maybe it would have a different effect, but I'm not going to go back and do that again. But the photon flux accelerated, didn't contain the movement of the smoke particles. Being unable to fabricate anything better at a reasonable price at this point, I'm kind of done with this project, at least for now. But maybe once this video gets posted on the BA YouTube channel, some LED strip fabricator company will try something, or maybe the people that make the individual LEDs will try something. But in the meantime, done with it. And then the stuff that I changed from last time. And then if you want to know, how small can you make LEDs? 90 nanometers. That's 90 billionths of a meter. You can make them in near infrared, 675 nanometers, or green, 525 nanometers, using perovskite LEDs. Okay, comment, questions? Have you had enough of this project? I have.
Question.
Yes.
If you use some length of fiber optic cable and shine the LEDs through that and bunch up the fiber optics kind of tight, would that also transmit heat, or would that reduce the amount of heat coming out?
You would have to put an insulated liner inside the fiber optic, because to my knowledge, there are no light emitting diodes that don't produce a certain amount of infrared, which is heat.
And that would transmit through the fiber optic.
Yes.
Yes.
Infrared, yeah.
Yeah, yeah. Okay.
Now, if you put filters on the front and back of your fiber optic segment, that would say the outside infrared can't be transmitted down the fiber. But if you have LEDs inside the fiber, those are going to produce some percentage of inefficiency and heat, and therefore move it. Yeah, I think it's a rich project for people with deeper pockets to play around in. Either LED chip makers or LED strip makers. I think that if you really can make smoke particles move based upon light, then you could make a fireman's mask that could make the light point outward. And if you got a high enough flux of photons that were bright white, you could actually push the smoke away from the air intake. So that might be something that's worthwhile, because then you wouldn't need a air tank, or the air tank would be drawn upon less because you'd be pulling non-smoky air in from the environment that you're in. Now, you might think, well, there's no oxygen in the room where the fire is. There has to be, otherwise the fire wouldn't be burning.
The fire would go out. Yeah.
Yeah. So there is air, there's heat, and there's smoke. And the heat you can deal with because you're wearing clothing and a mask. The smoke you can't deal with, you have to filter that out. And therefore, you either have to completely cut off your outside air source and just run off the air tank, or you have to have the big face rig that has the big cylinders on the outside that are particulate filters to keep the smoke from going out. And this might be something that will make it where those filters might last longer, but it does require power. But these things run at very low voltage. So, if you design it right, if you make it the correct efficiency level, the batteries might last a good long time. Because you may
wouldn't you also have to cool that oxygen or that air because that room is probably
Yes,
extremely hot?
yes. But luckily, they have these things called peltiers that you can pump electricity in one side and it will reduce the air temperature. This is what we used in amateur astronomy cameras to cool down the imaging chip until in Florida they can develop ice on them. So a small enough area with a peltier could reduce the outside temperature considerably. It's a mixture of sciences.
Yeah.
We used to have this situation where you go to make something and you make it based upon either things that are already tried and true or the things that you know. And it's only been, I don't know, in the last 15, 20 years that people that go to make something reach out beyond to see if there's things they can pull in to make what they're doing better. The common term for that is metamaterials, where you go grab something that you want to make and then you adapt some principles of physics at the nanoscale level, at the billionths of a meter scale, and it's very effective for doing things that are at the macroscopic level. How about metamaterial fireman's masks? Yeah, okay. Could be a whole new business out there. And, instead of selling the inexpensive masks to the local fire department and to, emergency rescue and to federal agents and such, you can sell them the expensive stuff. It's got moving parts. No, it doesn't have any moving parts. It's got electronics in it. Yeah, it does. And it's got batteries. You got to replace the batteries. You got to charge them. It's going to cost more, but it's better because it's metamaterials. Okay. Anything else? Otherwise, I'll stop recording. Hearing nothing.